Hello, good afternoon. I'm Tom. I work for CDN 77. We're a global CDN from Europe. I'm personally based in Prague, Czech Republic. And today I'm going to talk about the challenges we face when we try to deliver low latency live streaming without compromising the video quality and streaming stability. So I'll approach this from the CDN perspective. So I'll mostly talk about the signal path and the optimizations we do along the way. And then I've got a few ideas on top about transcoding as well. So the major question here is how low we can go. What do I mean by low latency? And in our case, I'm talking about the overall or glass-to-glass latency of less than 4 seconds. So I guess you all know what glass-to-glass means. It's the time between the real life happening in front of the camera and the playback. So, and to make it slightly more complicated, it's not the only delay we care about, because we chase down the glass-to-glass latency. We always need to make sure that we do not ruin the first frame latency, which is an important user experience metric, so startup time. So how quick you see the video from the moment you click the play button. And the latter metric should be always ideally measured in milliseconds. So I'll stick strictly to HTTP. So in terms of protocols, you can think of MPEG- and HLS. Even though low latency HLS is slightly more complicated due to the standardization, but we do all. So why do we have latency at all? Because the limitation is not the protocol itself. In perfect conditions, you can get below 1 second with HTTP, but the fun begins when you need to move the data across long distances and scale it. So this is the standard live streaming workflow diagram that you've probably seen many times before. It starts with the ingest and transcoding, packaging, then the delivery part, and it ends on the client side with the player. So to put it very simply, if you do not care about latency, each of these units can have sufficient buffer, and the whole process becomes very fault resilient. But so you can think of network buffer, read-ahead buffer in the player, and so on. But when you reduce the buffer, then the workflow becomes much more sensitive to any data or network data transfer or network instability. So that's actually why we still keep that 3 to 4 second window if the use case allows, because it gives us some breathing space, for global delivery and last mile issues and mobile networks, etc., etc. So the challenges it brings are widely interconnected, and it's pretty much all about how quickly we're able to process the content and how quickly we're able to move it across all CDN layers and to users. So now I'll share just a couple of ideas for transcoding setup, and then we'll get into the optimization that we actually do on the CDN level. So I actually realized that transcoding is not always easy outsource, not always outsourced to CDN, but still, when we do transcoding, we're faced with big setup questions. So I'll share just 3 of them as an example of what we do, and the chances are that you deal with them as well. So do we use pull-based or push-based transcoding? In other words, do we automatically transcode everything that is ingested, or do we actually wait until a specific stream or specific quality gets requested by the client? Do we have to sacrifice video quality for the sake of latency? And where do we place the processing part? Can we save the latency by moving transcoding to edge, for example? So these are big questions, no simple answers. It's all widely use case dependent. So let's go through these. So with push transcoding method, you simply transcode every stream as it is ingested, and by the time the first user requests the video, you may have it ready at the origin level. So it has a positive effect on the first frame latency, and it works well for scenario where you can easily plan this transcoding capacity. But when you think of some mainly user-generated scenarios, you want to make sure that you only transcode stream or qualities that are actually requested, because with UGC you can have a long tail of stream that never get watched, then you want to make sure you utilize your transcoding capacity wisely. The disadvantage is that you're actually losing the advantage of having the stream ready at the origin level when requested. So, and even though it affects mostly the first user for each stream or each quality, it still can negatively impact your performance metrics in a large scale. With video quality, just very quickly, you're still balancing between bitrate values, encoder load, and latency, because when you want to squeeze the transcoding process into, let's say, 20 millisecond window, you're likely to drop some compression optimization, primarily look-ahead algorithms. So in a way, you're losing B-frames because you don't have time to wait for some future frames. And without B-frames, you're likely to end up with slightly lower video quality at the given bit rate. And finally, for transcoding is HD solution. Can I cut down the latency by moving transcoding closer to users? And again, in some cases, yes, but it's not the ultimate solution, because we need to think, are we able to get the source locally as well, or do we still have to transfer the origin stream across long distance? Where's my audience? Is it local? Then fine. Is it global? Then we might end up transcoding single stream multiple times, which may become very costly. So many questions, not simple answers, trade-offs, and we haven't even packaged a simple single segment until now. So let's move finally to the CDN. By the way, meet Tom. That's our engineer. He's a real person. So in terms of software optimization, there's a large pool of features that we use and combine. But essentially, it all comes down to the ability to serve and store segments before they are fully created and cache them before they get requested by a client. So what it means, let's do a quick recap of how the video segmentation work. So we probably all know that CMF is a continuous stream broken down into small segments. They can be between, let's say, 1 to 10 seconds in duration. And these segments are then requested by or fetched by through MPEG- or HLS manifest. So one way of, or one method of cutting down the latency is actually shortening the duration of these segments. And it's a valid method, and at least based on our experience, you can get close to a 5-second mark for glass to glass just by doing that. But when you want to go even lower, you might run into trouble, because for us, those segments are actually the smallest addressable units. And what it means that each unique segment means a new request to origin. So what do you do by shortening the segment size? You're actually increasing the load to your origin, the number of requests. And more requests means more load, higher more HTTP overload, and more round trips. So you want to avoid that. And at the same time, each segment has to start with a keyframe. So when you go, let's say, below 1 second for those segments, you might have to reduce your GOP size, and eventually you end up with more data to transfer, which then means that you've got lower quality per given bitrate unless you're willing to increase that. So instead, we actually rely on the ability to transfer the data to the next layer before a single segment is fully created. So that process is called HTTP chunk transfer, and this effectively breaks down those segments into even smaller units, and we may call them chunks. And instead of waiting until the full segment is created, we can actually deliver those small chunks as they are created, and they can be as small as several milliseconds in duration. So from HTTP perspective, when we receive a request for an incomplete segment, we do not reply with 404, or we do not wait until the segment is fully completed. We just serve it partially as it's being created. So when you work only with completed segments, you always have to wait until the full segment is completed, and then only then you upload it to client. And basically, the segment duration is then added to the overall latency, because you have to wait the whole time. when you actually work with segments, when you upload those segments continually, so we basically create kind of a hybrid of file-based request response and stream-based, as just as we use in IPTV. And to be able to do this, we actually have to teach each and every unit in the live streaming workflow to serve and store incomplete files. So just think of your origin. You know, most market standard solution won't actually allow you to upload file without knowing its size and read a file before the upload is fully finished. So we usually end up with custom origin implementation that serve data from memory. And the following same principle, we move the chunks across the entire caching infrastructure, no matter how many caching layers there are. So the principle is always the same. And as soon as the smallest playable unit or those chunks are actually created, we pass them to another level. And then we need to enable the CDN to cache these incomplete files. So we use methods such as request coalescing and so on. And the real strength comes when we combine this HTTP chunk transfer with data preload. And what it means that with the knowledge of the next segment or following segment URL, we can use, for example, HTTP push and actually preload the segments before they get requested. And even when we initiate a data preload for a segment that has not been even partially created, we do not answer with 404, but we wait until the first chunk, the small playable unit is created, and we pass it forward. So the goal here is that by the time a piece of video is requested by the end user, we should have it somewhere, you know, as close as possible to the user, somewhere in cache. So it's not a new idea; it's a standard prefetch, but we now use it in this dynamic, you know, data transfer for live streaming. Another thing I didn't include in my slide, but I just realized it when I saw Mike's presentation on Quick earlier this afternoon. We actually use, you know, zero RTT protocols like Quick to eliminate round trips, and because it massively cuts down the first frame latency compared to, you know, methods such as TLS and TCP. Then getting to caching infrastructure, your CDN should ideally have multiple caching layers, with the first one as close as possible to the origin. You probably want to do a redundant PNI with your CDN provider, and the same thing applies obviously to the edge layer. It should be as close as possible to the user. And the idea here really is to eliminate the dependence on the public internet completely, which leads me to the network itself. And I'm deliberately using this picture because as a CDN, we're often guilty of showing you these pictures and boasting about how many POPs we have, how dense the coverage is. But it's fine, but it doesn't tell the whole story, because especially in low latency live streaming scenarios, the way we transfer the data between the origin to the CDN edge, so the internal network, is equally important, because with these low latency transfers, the cache is not efficient. And what it means is that the cache servers help us to reduce the load that goes to your origin. It helps us to amplify the content and scale it, but it doesn't really save the performance or content availability when the line between origin and within the CDN breaks. So just to get an idea how this works, consider a VOD scenario where you have cache hit ratio of, let's say, over 95%, and if the cache fill breaks for, let's say, 10 seconds, nothing really happens, because, you know, vast majority of your content is still delivered from cache. But with 4-second window, with less than 4 seconds between real life and the playback, you don't have that luxury. So even a small, you know, network instability can actually impact the performance. So we need a constant data flow between the origin and the user. So for us as a CDN, this makes us kind of revisit the state of internal network, backbone capacity, backbone redundancy, and convergency, so how quickly we're able to identify issues, how quickly we're able to resolve them. And in a way, it's not just about how close we're to users, but more like how well we connect the source with the user. So in conclusion, the technology allows us to deliver HTTP with low latency live stream, but it forces us to be super efficient with the data transfer to make up for the comfort that the high latency gives us thanks to those buffers. And with that, I guess we can call it a break. Thank you.